Okay. Yeah, that picture was on Castle Peak. That's Mike and Mike up there on a very windy day when we were up getting the hop site working from Vail towards Sunlight. Was that the other site, the next site down the road? And so I'm Dave Maciorowski, WA1JHK, and I'm going to talk today. I'm going to tell you a story today about the day that the voting receivers on most of the systems in Colorado and most of them in the world eventually took us all the way back to 1970. It was a really interesting investigation. James called me one day, and in fact, it was January 1st or 2nd, and said, "Gee, my receivers aren't. One of my receivers is offline, and what? I'm kind of stuck. How about we work on this together?" And so we dug into the source code and started looking at it. And think of it as a Y2K bug, but 21 years later. And we'll look at what happened here and some of the background. I'll look at how these radio thin client modules that we use for remote receivers that are used on the connection are used by NCARC on some of their systems. Lark uses them. The Fun Machine uses them. So it has some broad. It had some broad impact. We'll also do an overview of receiver voting and time, and how time is first of all, how is time delivered to the RTCM, why it's important, what got broken, and how we fixed it. But as a review, if you got a tall mountain or a tall tower, here ours are made out of rock, and your line of sight, you've got a pretty good signal in and a pretty good signal coming back. Here in Colorado, it's quite common for many of the repeaters to be one mountain back. The foothills can get in the way, especially when you get into the shaded area. If you drive west across Denver and you get over near Bandimere and along Morrison on C470, you're in a shadow. And if you're trying to work Thornton or you're trying to work one of the squaw repeaters, then you're going to have a hard time hitting the repeater and to a certain extent hearing it, but you probably hear it better than you're actually getting into it. One way to deal with that is to put a remote receiver. We've got, in this picture, we've got a remote receiver that is mounted on the hill in front. So now your line of sight to the repeater's receiver, even though the repeater's transmitter is back here on this other one, you're probably hearing it pretty good, or at least nobody has to listen to the picket fencing and the other distortion, the multipath distortion on your signal, but you'll just have to deal with that on the repeater. And especially with low power radios, with a handheld, this really improves the coverage for handhelds in the less coverage areas. So again, this way the repeaters are in the best signal, the best quality of the signal, and what can be tricky is getting the level set right and getting the audio quality set right. But there is some hardware that helps with that, and we'll talk about that here in a second. Typical repeater just has one receiver, one transmitter. Take for example the one of my repeaters up on Squaw, receiver and transmitters both up there. If you can't hit, if you can't transmit a signal that's going to reach all the way to squad, then the repeater's not going to hear you very well. But by adding additional voted receivers and spread them around to different areas, then the receiver with the best signal is going to be selected by the voting selector. And here in this picture, you can see we've got 3 receivers. And as let's say you're driving around, not line of sight to the repeater, or not always line of sight to the repeater, you can see how the different how much of your signal is getting into each one of the receivers. And I show full scale, half scale here as an example for how the voting selector would vote. But what's important here is that the audio samples must be aligned in order for this to work. And that's where the timing comes in that we had trouble with back at the first of the year. So what we do is we deliver the aligned audio from all the remote receivers to the main site. And we do that using one of a couple of gadgets. The one on the bottom is called a radio thin client module. It was manufactured by Micro-Node International, who is now out of business. In fact, their website disappeared too. The one above it is the original through-hole version of that design, designed by Jim Dixon, the original author of All-Star Link. He's SK, but his design lives on. There's references at the end of the slide set that take you right to the CAD, for example, for that upper board if you wanted to experiment, or to the source code if you wanted to make changes. But these boards are basically equivalent. They provide a radio interface. They provide a GPS interface, and the GPS is going to be the important part of the solution for aligning those time samples. We have a network interface. We're going to use Ethernet for delivery of the samples. We're going to use a network communications protocol called the voter protocol. We're going to these modules also provide the ability to set levels, set the squelch, and there's also a fallback capability. So if you have a receiver and a transmitter both hooked to this and the network goes down, you'll still have local repeater operation. Peering inside this thing is a microcontroller. You've got an A to D for digitizing the audio, a D to A for getting it back to analog at the other end, and a GPS. And we digitize the audio. We also generate a signal strength indication or a signal quality indication that is used by the voting selector, so that it takes the best of the signals that are presented to it. And my example, I showed 3, but it could operate with 2, it could operate with 20. And the solution scales pretty well. We use I mentioned the voter protocol. The voter protocol is used for transferring the sampled audio, the timestamps, and the signal strength. And I'll have an example of that coming up. There's also some other packet types that are used for configuration and as a keep alive on the network. But primarily for voting receivers, it's the receive audio that's being fed. And so the way that works is the RTCM will sample audio every 125 microseconds. So it's 8,000 samples per second. And every time it gets 160 samples, it puts a timestamp on it and it sends it up to the voting selector so that the voting selector can make use of, it can look for the best signal and then select the one that it's going to provide to the transmitter. And this is what a packet looks like. And notice what I highlighted here in yellow. What's highlighted in yellow is the timestamp, and it's kind of an odd looking number, isn't it? Well, it's the number of seconds since 1970. And there's some obscure history about that, and I'll touch on that again here in a second. What we need to do is we need to make sure that every one of those receiver sites is getting good solid time. So we use a GPS receiver at each site to deliver those timestamps. And then using the protocol we just showed, we're going to send those samples with the corresponding timestamp, those samples with that timestamp on it, up to the voting selector. And notice the numbers here on the Ethernet path. From the main receiver, it only takes probably less than a millisecond to get to the voting selector, the receiver selector. The second one might take 25 milliseconds, and the third one might take 160 milliseconds. So the flight times are different, but they're all going to have the same timestamp on them. So when the samples are received, they're received out of order. And what the voting selector has to do is it has to align those buffers so that it can compare apples and apples. It can compare the samples that all happened at the same instant in time to all the other samples. So it has a buffer, and this buffer is aligned using the timestamp for all of the samples that have come in. And then it compares the signal quality, the RSSI, to select which one of those buffers is going to be sent to the transmitter for that 20 millisecond time period. But what happened? If you think back to Y2K, there was a great panic in 1999 over what's going to happen in the world. Are planes going to crash? Are trains going to crash? What bad is going to happen? Well, you know, part of that was due to the way the date was stored. Everybody assumed, oh, 1900. We only invented computers in the 1900s, and maybe we won't have them in the 2000s. So when it rolled over from 99 to 00, the computers assumed that was 1900 instead of 2000. That created quite a number of problems. I did some consulting back then to investigate whether some of the systems would have problems. But what the RTCM does is it uses a C library call that manages the time in seconds since January 1st, 1970 at midnight UTC. And, you know, yeah, that's a lot of seconds. And that's where that number came from that I showed a few slides back, and I'll show here again in a second. For example, there's an upcoming Y2K plus 38 date coming in 2038 for any system that calculates seconds from that starting point, January 1st. If you used a 32-bit signed integer, we're going to have another Y2K event in that year. So where did the January 1, 1970 come from? Well, computers use an epoch as a fixed starting point to calculate relative offsets. And, you know, depending on your system, different designers use different epochs. Jim Dixon, the original author of the firmware that's used on the voter board and the RTCM, decided to use the C library, which kind of surprised me because C library isn't known for being efficiently coded for small microcontrollers. And so he used, because of that decision, he ended up using an epoch of January 1st, 1970. It's some of the C library routines were coded with integers, and that's where the 1938 year for the next event comes from. It's if you just use an unsigned value, you get another 2 billion seconds, so it pushes you out into 21 something. Sometimes developers have a hard time thinking forward like that. Yeah, hardware is not going to last that long, right? It ages, it quietly fades away, but the software, it's the software, right? Software is going to live forever, and it just keeps getting ported forward onto a new platform. I've always said that it's way less expensive to jack up a piece of software and run it on a new piece of hardware than to rewrite the software from scratch. So where the RTCM gets time is from the GPS. The GPS stream, let's see, the GPS receivers generate NMEA ASCII strings. There's a ton of them. The RTCM happens to use this one, the GPRMC string. And you can see right there in that string where the hour, minute, and second is highlighted at the beginning, and the day, month, and year later in the string. What MakeTime did was it took that string as input, decided that it couldn't comprehend the data, and returned an error of -1. Well, if you take -1 and you run it through, there's another complementary library routine called CTime. It prints out January 1, 1970. And correspondingly, this value of -1 then becomes the value that gets sent down the network to the server and the voting selector. And the voting selector can't handle a 50-year discrepancy between its time and its remote receiver's time, because the buffer is only 1 second long and it can't tolerate 50 years worth of seconds. So that's what caused the overall problem. It caused the receivers to drop offline because of this major discrepancy between the time stamp that's going up the network in the packet and the time that the voting selector already had available. The fix is an eye chart. If you really want to see it, of course, it's readable on the slide. It may not be reproduced well over Zoom, but I'll post the slides and you can take a look. One solution for the problem was, well, I could have gone and looked for a C library that had the bug fixed. As a developer, and I've developed software for a very long time, that scares the hell out of me, especially on an embedded system, because if you pick up other routines out of that library, they might have some new bug, or there may have been a bug that the embedded code was working around, and now with the fixed code, now it's broken a different way. So instead, I took a direct approach, and I started with an epoch offset to January 1st, 2021 at midnight. And then I just added seconds from that point forward. Seconds on that day, current month, current year, leap years, don't forget the leap years. So my solution is good out to 2099. Once again, am I looking far enough? Well, I don't know, maybe. I suppose I could look at centuries and and make it good till the year 3000, a Y3K bug, but I didn't. I got lazy and I did through 2099. And here's the confirmation, right? The corresponding string, you take the time out of it, and sure enough, C time converts back to exactly the time that you expected it. And I found a couple of online references. If you go to either of these, you can put in a duration between two dates and times, and it'll tell you the number of seconds between them. And that's what I used for validation. In fact, I found a bug on one of these tools. The timeanddate.com had a leap year bug in it that they've now gone back and fixed. But I stumbled across that while I was validating the solution, because those web pages allowed me to put in 2099 as a year, and I could calculate the number of seconds all the way through to there, and I made sure that my algorithm did it properly. So validation is always an important point. And that's the end. Here's some references that'll take you to background information on the technology, and also the source code for the voter, as well as the CAD file. So you can actually, and I noticed on, was it Osh Park? I was on one of the PCB vendor websites yesterday and noticed that they already have the board files up on one of the sites. All you have to do is click order, and you can order boards. You don't even have to upload the CAD files. Any questions?
Well, this is why you need modelers to write code, because we have models that goes 2 or 3 or 4,000 years into the future. So our time and date routines work for any date.
Yep. Yeah, one of the choices I made, remembering this is a 16-bit microcontroller, I made the choice to stick with variables that weren't bigger than a D word, so that I wouldn't burden the microcontroller in two ways. One is I didn't want it to take a lot of time, because this thing runs on the tick, right? Every 20 milliseconds, it's got to send 160 samples. So I made the choice to restrict it to a D word in this case.
So, okay, this is Dan Fay here. 20 milliseconds, how did that time slot length get picked? Because I've seen 20 milliseconds a lot with kind of voice stuff.
Yeah, that came out of, I think, the VoIP commercial products.
Okay.
And as it moved to radio over IP, they stuck with it. Trying to think of the name here. So Jim Dixon was one of the guys that developed Asterisk originally as well. And of course, All Starlink is layered on top of Asterisk. So that just propagated out to these receivers as well.
Yeah, because I noticed Codec 2 seems to operate in multiples of 20 milliseconds as well. Just wasn't sure what I mean, it's a reasonable number. I just wasn't sure where that originated.
Yeah, I think that's where it came from.
Okay.
Hey, Dave, this is Mark. I just had a, kind of a question, in terms of the, there's a transmit buffer link on the RTCMs. There's also a buffer link that you can put in voter.conf in some different places, and they're kind of different the way that they're calculated and so forth. With your experience, what's the best way to go through and take a look? We may have some that are on VPN, we may have some that are point-to-point microwaves. Do you have any thoughts or recommendations on going through and validating that you've got the buffer links set correctly on the RTCMs as well as the asterisk instance? I'm just kind of curious on that.
And I think it boils down to what's the worst case latency that you're going to expect. I know there's been a lot of trouble with Akron because it's way out on the end of a VPN and then a couple hops. And if so, you look at the worst case latency on your pads, and you need to be able to either tolerate that or come up with a better communication scheme in order to deliver the audio packets to the voting selector, to the All-Star Link node in this case.
And I thought the Akron, though, part of the fix with that was to run another instance of asterisk. Apparently, asterisk to asterisk is more tolerant than each of the clients going through, my understanding.
Yeah, and it's not a voter either, so you're not restricted to the voting path.
I think that's the key, is if you're voting, any